All right, guys, let's get started. So this is the last part of SVM and last session of our course this semester. As you might have seen my announcement, I'll be at the library of ACE department, the second floor, from 3 to 4 if you had any questions. So I'll be there today, my office hours. So make sure you take a look at those practical exams and solutions that I posted online last week for SVMs. Your exams questions wouldn't be that much harder than those. So, all right. So let's just have a recap of what we discussed last session. So we talked about Lagrangian duality. We talked about how we're going to start from the primer problem in optimization, which was this problem, for instance. We wanted to minimize a function called f of x given some constraint, which we call it subject to, or ST, right? So in optimization theory, there is another way to look at the same problem by defining the duality of that problem using a Lagrangian function, right? So that we use this property in order to define a Lagrangian dual for our primer problem, which is going to be this. If you have such a problem as above, we talked about that minimization turns to maximization, and it's going to be unconstrained and subject to a new hyperparameter. We define it as u here, for instance, right? So in order to solve this problem, the dual problem, we need to have the gradients of this, right? Gradient of f of x plus the summation of all the j's from I to m, uj gradient of gj of x. So we use the same notation in order to define a dual form for our SVMs, and then we use the gradient to compute w and then alphas, right? So we saw that in the previous lecture. Okay, and then we talked about how we're going to define the Lagrangian duality for the SVM problem. We reached to the point that we had this function L of alpha as a dual form for the SVM, and then we had to compute the alphas. So the alpha stars would be the solution of the dual problem, which is, because of the duality property, is going to be a solution to the primal problem as well, right? So the final form was, we need to maximize this given this constraint that alpha n's are greater or equal than 0. And at the same time, the summation of alpha n's, y n's are 0, right? Also, we talked about how we're going to define these parameters in a vector space, right? And we came up with a P matrix and M matrix, which was a huge matrix of all the yn, yms. As a note, you need to make sure that this dual problem of the SVMs is also a quadratic problem in itself, right? So in order to solve this, you need to have a QP solver as well. All right, so that was our Lagrangian function here above. So in order to simplify that, we define it as L of alpha, half of alpha transpose M alpha and P transpose alpha. And then we define these two matrices. So M was this gigantic matrix of starting from y1, y1, x transpose 1, x1 up to yn, yn, x transpose n, and xn, right? So that was your M matrix, and your P was a bunch of minus ones and the bounds for alpha, which is the optimal solution for that optimization problem, is from 0 to infinity, right, given this constraint. So that was the dual problem of the SVMs. So now that we defined this in the previous lecture, how are we going to use this in order to gain some, advantages? Why do we need a dual form of SVMs? The answer is sort of intuitive, because if you recall previously when we talked about the linear models, when we wanted to apply a nonlinear transformation with those, the order became very complex, and in order to define higher polynomial orders, like, I don't know, second order of polynomial, third, and up to Q's order, you need to compute that specific order, and it would be a very complex problem if you wanted to use it in your training set, right? So say you had this data, like you had pluses here and you had minuses there, right? In order to compute higher order of polynomials, just go like this. Say you had other minus there, right? So this requires higher polynomial order, right? So now using this duality form that we defined, we can apply kernel functions to avoid computing this higher order of polynomials. So this process is called kernel trick, and I'll showcase you in a few slides. And that's the reason we need a dual form for SVMs, because at the end of the day, the solution, the alpha star of I, which is the solution for here, and actually this is the solution for the dual form, and also given a dual form, we can compute the solution for the primal form, right? So we have the same solution, but if we convert our primal problem to the dual problem, we can use kernel tricks to do this nonlinear transformation easier, and I'm going to show you in a few slides. So let's talk about the decision rule. So how are we going to define those classes, minus 1 and plus 1, right? So we need to have an estimate of y, which is called y hat, and it's a sign of W transpose x plus b, right? Given that W comes from the alpha n star that was the solution of the dual problem that I just mentioned. So in the previous slide, if you use a QP solver and you find the alphas, using that alpha star, now you can compute the W here, right? And using W, and then the other constraint, you can find B, and when you have W star and B, when you have W star and B, you have the answer to your SVM's maximum margin of the decision rule, right? So this is the way it goes. And we knew that before, that Ym, this should be equal to 1 then through this, right? So this is a process in a high level. Any questions for this? This is like backward. Then okay, so now we know the general process. First, we find a dual problem, we solve it, we find the alphas. Using the alphas, we compute W. Using W, we can find B star, and then using these two, we can define the sign of the decision rule, right? So this is the process. It's obvious now. Now let's see how we're gonna take use of the duality here to define kernel tricks for higher order of polynomials. Yeah, so that was a support vector. All right, so if you take a look at the dual problem, it depends only on x1 up to xn through xi transpose xj's only. This is a very key observation. So that means that the decision rule that we need to find for SVM, the maximum margin, depends only on xi transpose and x's, right? So if you recall this, so we had this nonlinear separable data set, right? We have pluses and minuses here. So we need to have such a shape, a circular shape, in order to classify this data, right? And we apply a nonlinear transformation called Z that does this square for both of the axes, the both parameters, x1 and x2. So Z transform x1 and x2 into x1 squared, x2 squared, right? So we're going to have this as our new transform axes, z1 and z2 space, where we have pluses and minuses separated, right? And that was the line in which classified these two, right? So decision rule depends only on xi transpose x, right? Let's see how we're going to use this with the duality and avoid extra computation of higher orders. Okay. So in general, suppose we apply a nonlinear transformation, right? So we want to transform our x's to a z space, right? And then we would like to apply SVM on the z space, on the transformed space, right? So we want to accomplish this. So if you find a dual problem, the Lagrangian form of alpha, right? In order to compute SVMs in a transform z space, right? We need to compute this only, z transpose n zm. So you see that in order to compute that, it's going to be pretty easy because it's just a matter of inner product of two matrices. And the complexity of the optimization is essentially unchanged because it's just this is just an inner product, right? So that gives a huge advantage to SVMs because of the duality property, because you can define a higher order of polynomials easily, like a classifier like this that can classify all the pluses and minuses easily. I mean, not to overfit, but you see this is this has a q could be anything like 8, 9 order of polynomial, right? So it can easily classify this nonlinear separable data set after the transformation to the z space, right? And you see that in a z space, we can just compute this by an inner product. So the complexity of the optimization essentially unchanged. Right? And this method is called kernel tricks. And this is one of the well-known usage of SVMs. One of the key factors that they are famous for is SVMs are enabling us to apply kernel tricks because of the duality property, so that we can transform to a z space and apply and compute the z matrices, z transpose and zm easily, right? And as you recall from the first lecture, the cross-validation error of SVMs are only dependent on the number of support vectors, right? So we can call it easy inner product. Okay. So essentially, if you want to compute in X space, right? Previously, if you wanted to compute the cross-validation error, it would be equal to the number of support vectors divided by n, right? Which was small because normally not all of your data set in n are support vectors. For instance, in this case, you had only 2 support vectors. So the upper bound for the cross-validation error is a small and reasonable amount. So combining this, you see that SVMs can be such a powerful machine learning tools because their generalization is pretty much not very complicated or not very complex in if you take into account the computations that are needed to come up with a model for higher orders. Okay. So and that leads us to define kernel methods. So we have the X space. X was, in this case, we had 2 x1 and x2 only, right? We wanted to transform to a z space using a phi of x function, right? Suppose we wanted to transform it to a second order. So what we needed to do was to compute this function 1, x1, x2, x1 square, x2 square, and x1 multiply x2, right? So this would be equal to compute this z transpose z prime, which is 1 plus x1 x1 prime, x2 x prime, x2 prime, and so on and so forth up to x1 x2 x1 prime x2 prime, right? So now we got a question here. So the question is, can we compute k of x and x prime without having to compute z and z prime? Does anyone know the answer? So we would like to have this, right? So can we compute this without the need to compute both the Z transpose and Z prime. Does anyone have any clue? Because Z prime is the evil now, right? It requires a lot of computations. Okay, so you'll see the answer shortly. So suppose you have your k as x and x prime, which was equal to 1 plus xt x prime square, right? So in order to compute that, you need to expand this, the first one square, the second one square, and then you have 2 multiply the first one and the second one, right? So this is the expansion of that. So each of them square. So call this A, B, C. So that would be A square, B square, C square, and 3 other components. 2 multiply AB, AC, and BC, right? So that was the expansion of that. So in order to compute, instead of computing Z and Z prime, now we just need to compute the inner product of these 2 matrices, right? So now, in this case, I don't need to compute Z prime directly, but rather by just the computation of an inner product of these 2, right? And this is a very good and efficient way. Right? And the output of this is just identical to a quadratic transformation. So now instead of doing all those computations, I'm just going to have to, depending on the order, what Q's order we're talking about, I'm just going to expand this and compute the inner product of these 2, right? So I'll give you an example in the next slide so you get the idea better. Okay, so let's go for a polynomial kernel of order of q. So now we want to find the qth order of polynomial for this, right? So we would like to find the z transformation of qth order. If you were to do it directly, that would require you to compute the z and z prime, which was a computationally intensive transformation, right? Qth order. Rather here, we expand this depending on the order, and we can just find the inner product of the qth order of polynomial transformation, right? We can also apply some hyperparameters here to regularize the process, like this omega here. I'll show you a second order example in the next slide. Okay, so let's see the example of the kernel tree for So let's take a simple case in which the omega was 1 and the dimension was 1 as well. So you're going to have to compute the exp of minus x prime squared, right? That would be equal to computing this e minus x squared, e minus x prime squared, and a summation of all the k's from 0 to infinity of 2 to the raise of k, x to the raise of k, and x prime k divided by k star. So that's the nonlinear transformation, right, for higher orders. So instead of computing the z directly and z prime, I can expand this easily to whatever order I was interested in. That's why I put these 3 dots, because this goes to the higher order. Qth order, right? goes on and on and on. So you start from 1. This is the expansion series. So the square root of 2x divided by square root of 1 factorial, and this goes on with the 2 factorial, and you have to compute the z prime, the same parameters but in prime form, right? So instead of computing these two directly, we know how we're going to expand this by the order we are interested in, and we just compute the inner product of these two, right? And that's what is called the kernel trick in SVMs. It's going to simplify the way we can find the higher order of polynomials to solve our problems by defining the Lagrangian duality. You don't need to memorize any of these expansions. I mean, this is just a high-level overview of how you can use kernel trick in SVMs, right? So just don't get freaked out by seeing this. All right, so to sum up, although z is infinite dimensional, right? The transform space is infinite dimensional. The kernel function is easy to compute. So that's the whole purpose of doing kernel tricks. That's why generalization is very efficient in SVMs. You find the Lagrangian duality, so the Lagrangian dual function, right? And then this only depends on Zn and Zm through k xn xm. And that's the actual trick. So instead of computing Zn and Zm, we compute it through k x of n x of m here. So that was the whole purpose. And then you can compute the W's for the support vectors using the alpha where you have your b equal to ym minus the summation of alphas alpha n, yn, k, xn, xn, right? So that was the whole kernel trick. Let me just double check something here. So I fixed the typo here. So this was Zn here. Your W's that was Zn instead of n, right? So using kernel trick, your Zn and Zm only depends on k of xn and xm, right? And using that, you can compute your W, and then you can compute B. Then the final sign would be this. And that was a kernel trick. All right, guys. So we're literally done with the SVMs and the course. Hope you had some fun this semester. Hope you learn at least a thing or two about machine learning. You're going to use it in your future career and get the highest paid salaries, probably easier. I'll be at the library this afternoon 3 to 4. If you had any questions or any concerns about the course, just come talk to me. And meanwhile, if you had any questions, just email me. I'll be happy to help you out before your exam. And make sure to take a look at the problems of SVM that I uploaded last week. The exam, just like the midterm exam, wouldn't be harder. This is just, you've been taught, this is going to be the same level as your exam. All right, so good luck on your exam. And yeah, see you next week probably. Have a good day.